The problem statement from GATE Physics 2022 paper reads as follows. For a bipolar junction transistor, which of the following statements are true? Option A. Doping concentration of emitter region is more than that in collector and base region. Option B. Only electrons participate in current conduction. Option C. Current gain beta depends on temperature. And option D. Collector current is less than the emitter current. This is a multiple choice question with more than one correct answers, and we'll try to find out the correct answer or answers. The term bipolar junction transistor consists of three separate words. The word transistor means any device in which a third terminal controls the current flowing between other two terminals. So let's assume these are the two other terminals, X and Y. And if we were connect to, let's say, simply connect a tube between them, the water will flow, right? But that's not the case. So here we are deliberately introducing a barrier like this. So you note that the height of this barrier is barely above the water level on the left side. Now what will happen, since the water level is just barely above the barrier, so the small amount of water will flow. Now let's say somehow I am able to reduce this barrier. So what will happen, the water level remains the same, but more, since the barrier is lowered, more water can now flow. What happens if I raise the barrier? So if I raise the barrier will go above the water level, and thus no water can flow. Now note that although the water level is same in all the three cases and the elevation between left and right remains the same, it's the barrier which is controlling whether the water flows or not, and if water flows, how much water flows. This is the analogy that we can use in devices also. And this type of behavior is known as a transistor, where third terminal is controlling the flow between two other terminals. The second term in BJT is junction. What kind of junction we are talking about? We are talking about P semiconductor and N semiconductor junctions. And the word bipolar means two poles. Bipolar, two poles. What are the two poles? Electrons and holes. So the current in a BJT is due to electrons as well as holes. Both of them contribute to the current. Now, depending on how you join the PN junctions, you can have two flavors of BJTs. One is NPN BJT and the other is PNP BJT. We'll be focusing more on NPN BJT. So NPN BJT has electron as majority charge carrier. This means a majority of the current will be due to the flow of electrons, and very small amount of current will be due to the flow of holes. Right, and this is how the schematics of BJTs look like. So you have an emitter, you have a base, you have a collector. Emitter is N plus type, base is P type, collector is N type. Okay, now what do this N plus denote? This denotes that emitter is heavily doped. The doping in emitter is high. Why is it high? Because it has to provide a lot of electrons. The doping in base is low. Why is it low? Because so as to facilitate, most of the electrons that are injected from emitter to the base, they go to the collector, they do not recombine in the base. If the doping of base is high, this means number of holes is high. Most of the electrons that are being sent by emitter will die in base itself and will get very less current at collector. We don't want that. Hence the base is low doped. Collector can be moderately doped. On the other hand, the width of base should be narrow, because we want very less time for electrons to spend here. The less time they spend, the less they will recombine. So base should be narrow. Collector should be wide so as to dissipate a good amount of heat. Heating has bad effects for any device, so we want collector to be wide so that more heat is dissipated more efficiently. And emitter can be moderately wide. Now this is the NPN emitter base collector in equilibrium. Note that there are barriers here. You can see that there is a barrier to the electron flow. Electrons cannot flow easily. However, if we bias this NP junction, note that this is N, this is P. N is heavily doped. This is denoted by N++. So if we dope this as forward bias, this means N is connected to negative and P is connected to positive. This NP, correct? Then it is forward bias. Then this barrier will be lowered and a huge amount of electrons can flow into the base. And if I bias this NP junction is reverse biased, N is to positive, P is to negative, this is reverse biased. So there will be a huge depletion region here, and the electrons, if they successfully pass through the base without recombining, a small amount will recombine. As you can see here, small amount will recombine, right? Because there are many holes here. A small amount will recombine, but if we ignore them, you can see the heavy majority of electrons which are being diffused into the base can simply drift across the depletion region on the here, and they can reach the collector, and we'll get our collector current. So this is how the whole circuit diagram is. This is the working of an NPN BJT that we have seen here. A small amount will recombine, I re-emphasize that, and that's why we say that the current in a BJT is not just due to electrons, because some holes are being recombined, so it's being resupplied from the battery here, and hence the current flow is due to electrons and holes, and also some holes will diffuse from here to here. So the contribution of current from holes is there, but it is very small in a NPN BJT. And this is nothing but a KCL if you apply here. So IE is current, electrons are flowing here, current will be flowing out. Similarly, if holes are flowing here, so current will be flowing in. So IE is this, IB is this, and electrons are flowing here, so current will be opposite IC. If you apply KCL on this BJT, it will be current flowing out, which is IE, which is equal to current flowing in, which is IC plus IB. This is the expression, and this is what we call the current gain, beta. Beta is the current gain, which is nothing but IC upon IB. This is the mathematical expression. Similarly, we have another parameter called alpha, which is IC upon IE. So IC is the collector current, IE is the emitter current. This will always be less than 1, because some electrons will always get recombined here, right? But it's for a good BJT, it's very close to 1, so it may be 0.99 or 0.98, something like that. It's very close to 1, and beta is usually high. And this is all we're talking about in terms of the DC analysis. But that is not the complete picture. Beta is dependent on temperature, as you can see in this curve here. So we'll not get into the in depth that why is it so, but it's I can just comment that it is that as we increase the temperature, the beta, the DC gain, we saw the current gain, beta is nothing but IC upon IB, that increases as we increase the temperature. So we can see that beta is not constant with respect to temperature, and beta is not constant with respect to collector current either, right? Now we get back to the question. Questions asked for a BJT, which of the following statements are true? We saw that doping concentration of emitter, so doping of emitter is more than collector and base. We saw that, which is required, because it has to be the source of electrons in case of NPN BJT. So this option is correct. Only electrons participate in current conduction. This is not correct. We saw that electrons and holes also participate. Holes, because there is some back diffusion from base to emitter and some recombination, so holes also participate. This option is not correct. Beta depends on temperature. We saw a curve in which beta is dependent on the temperature. This is correct. Collector current is less than emitter current. We saw that alpha equal to IC upon IE, which is will always less than 1, very close to 1, like maybe 0.9, but it will be less than 1, because some electrons will get recombined in the base. So this is also correct. So for this question, the correct options are A, C and D. Thank you for listening.